Okay. I'm ready. Are you ready? So, today it's lecture number, who knows the number? Number 5. And I hope you are not too bored with the problem of diffraction by half plane, but we'll be solving it today again using another method. And probably after this lecture we can conclude that we went through the minimum through theoretical minimum for diffraction theory. So once you know all these ideas, you're ready enough to start to do your own research. Because there's a lot of things we can do, and I think we will continue for 2 or 3 more lectures. But those first 5 you should know very well if you want to do diffraction theory. And which is nice about all this mathematics, that all the ideas can be demonstrated on one standard problem. So the difference that we will be using so-called Wiener-Hopf method to solve the problem of diffraction by a half plane. Last time we did it using Sommerfeld technique, and that's how it was originally done. In his seminal work of Sommerfeld, did it. Sommerfeld, I think it was, and I'm not sure where it was done with Wiener-Hopf method, probably in 1930s. But we all know book by Nobel, so this method was extensively described, and the book was sold very well actually everywhere. You can see scientists from different countries who found this book and they are doing some research based on it. And the book, yeah, it's 1958. And probably you will never hear this name again, because the only thing this guy did is he wrote a book, and this book was based on lectures of Jones. So you probably heard who is Jones. If you did not, it's fine, but it's like a very, very famous mathematician. Yeah, but he has a very, I suppose, standard name. So this technique sometimes people say we will be deriving Wiener-Hopf equations using Jones method. But today we won't follow it. So for those who want to understand these ideas in more complicated context, I just refer to this book, and you can read first couple chapters quite easily, and it also discusses at first problem of diffraction by half plane, but I try to move faster today, so we'll be able to solve this problem within one lecture. So what do we have? As usual, we have our half plane. We have Neumann boundary conditions. Just to be specific. Then we have an incident wave. I won't discuss problem statement in many details because we did, and of course the problem statement remains unchanged. And we have what else? So we can have, we won't be using much polar or coordinates today, but we have. And the wave is characterized by angle of incidence. Okay, that's our statement. So anyway, let's be a bit formal, write some equations. So as usual, step one for us is to do the statement. We have Gilligan's equation everywhere outside the half plane. We have our field is presented as a sum of an incident and scattered field. So this thing should satisfy radiation condition. And okay, I hope the definition for incident wave is unchanged from the last lecture, but let me write it down. So here there is a tiny detail. I will suppose today that theta in belongs to pi over 2 to the following segment. So our wave is coming from this quadrant. And that I will use when I am poising with the radiation condition. So now I will have my radiation condition in terms of limiting absorption principle. So and where I suppose I have a real part of wave complex and I have a small imaginary part, which is positive. And by default, this limiting absorption principle will fail if theta doesn't belong to the segment. And we discussed it, I think, in lecture 2. And you can try to find a simple fix. Of course, we don't have these restrictions. Generally, so like one way actually is just to solve the problem thinking that theta belongs to the segment, and then our solution will be valid everywhere. You can just analytically continue it, and it will work fine. But another way, of course, we have problems with our limiting absorption principle because here we have the incident and also we have a reflected wave. So if we extract the reflected wave, we also won't have any problems. So here, just to stay simple, I will suppose this condition. But it's important when you start to solve things, you can like accidentally make some mistakes. So if you take theta outside of this region and you will suppose that you have a limiting absorption principle, you will get some problems. Either you will get a wrong solution, or you might get some exponential growth, so you will not get a properly defined Fourier transforms. So this is, I can say it's as a homework, if anybody does homework or wants to do any homework. I can say like problem 1, but it's like a very general question to think what changes. throughout the solution for other theta in. That's a nice small exercise. And of course we have mixing condition. So yeah, that's probably the last bit we need is mixing condition. I know I said it many times, but okay, we did this, and now our problem is well posed and has a unique solution. Okay. Then what we do next? Oh, I will probably use your picture. Then the second thing we do is symmetrization. That's a very useful little trick that everybody needs to know. And this problem has, like, the geometry of the problem has a vertical symmetry. So it has a symmetry of with respect to x-axis. If we reflect it, we will get the same geometry with respect to x-axis. Let's try to use this property to make our statement simpler. So right now I will just reformulate the problem in something which is slightly simpler. So what I say, let's present our field as a sum of symmetrical part and anti-symmetrical part. And to be very, very precise, I will say what I mean. So symmetrical part possess the following property. And somebody can guess what property possess the anti-symmetry. So I say instead of studying this problem, let's study two other problems. One is symmetrical. What is anti-symmetrical? So what do you think we need to do to make them symmetric and anti-symmetric? We need to decompose the incident field into symmetric and anti-symmetric part. And then since we have anti-symmetric and symmetric forcings, we have geometrical symmetry, then just our solution has no other option as to also possess these properties. So one problem will be like this. This is symmetrical. the second line will be very similar, but just with minus sign. So, what can we say? Okay, let me do one more thing. Let me write this thing. So, for our incident wave, we have the following representation. So a question: what can we say about this problem? Like what I will try to say right now, that one of these problems is much simpler than the other. Which one is much simpler? Do you have any ideas? What is nice about this incident wave? This wave satisfies boundary conditions by default. So it means that solution of this problem is trivial. Solution is trivial. Follows from the fact that it's given. So the incident wave itself satisfies the problem. Thus, we have no scattered field. So it's zero. And this problem is more complicated, of course, but it means that all our scattered field is antisymmetric. Make sense? Questions? It's okay. Good. So, okay, we didn't do much, but now we know some symmetry properties of our field. And we did all the stuff, and what I do, I say, okay, now I just consider a symmetric problem. So I have my incident wave here, and actually, since the problem is symmetric, I can consider it just one half plane, an upper half plane, and then build the solution in lower half plane by symmetry. So I drew this thing, but I actually removed it. So I don't care what's happening there, but since I removed, I need to put some boundary condition. And of course, since my field is antisymmetric, it means it should be zero at this line because of antisymmetry. So my additional boundary condition is U scattered is equal to 0. And here, if I state a problem for the scattered field, I have my condition like this. Or just some homogeneous condition for the scattered field. Cool. What do we do next? Okay, let's write down this thing. Boundary condition on the half plane, on the positive half plane. Because we will use it later. So nothing complicated happened. I just differentiated the plane wave and took its value on this half plane. So that's it. Okay. So now we can go to step 3. It's like step 3 of our lecture, but actually step 2 of the solution. And we will formulate Wiener-Hopf problem. Equation. So, as I said, there is a standard approach by Jones, which you can find in Noble's book. And just to make things less boring and more interesting, I will follow another approach which I like a lot, and it doesn't have a particular name behind it, but I will call it Green's formula method. So my plan, of course, is to apply Green's formula in the upper half space. So first, so what do we need to apply Green's formula? We need to choose a pair of functions and a domain where we apply our formula. So I will describe you the choice of domain, the choice of functions, and then once we apply, we will arrive to Wiener-Hopf equation naturally. And this idea can be used in almost any context, so it's very easily generalizable. That's why I like it. And it's also, you get to the equations very fast. You can open Noble, and you will see that he spends like at least 10 pages to derive his equation. So my domain, and here I will put actually, to be formal, I need to put a small semicircle around this point, the vertex of half strip. Okay, I have half circle, and here I have some like small radii epsilon, like this. And okay, let's apply Green's formula to this domain, and we take two functions. One of them is scattered field, and you can try to guess what is the second function. Of course, those who don't know. do you have an idea what should I choose as a second function or a good formula to get a Wiener-Hopf equation? If you ever heard about it, of course, before. No idea? Yeah, fine. But it's, if you don't know it. So second function will be, we don't have many choices. What functions we know? We know Green's function, scattered field, and plane wave. So I will apply my Green's formula with the plane wave. And that's a beauty. But now it will depend on spectral parameter. So why do I do it? Of course, when I will apply my Green's theorem, I will claim that the integration on a big arc tends to 0. I don't have any problems as epsilon tends to 0. Like somebody needs to check it carefully, but it can be done. And then I will left up only with the integral along x-axis, just on real line. And when I'm on real line, I just have this exponent, which is like, you know, a Fourier transform exponent. That's why I did this choice. So I want to have some Fourier transforms of my field, some spectral functions, which live on the boundary of my domain. And then I can study analytical properties of this function. But you know, let's do it step by step. Like formally, we discussed it before, but I need to choose like a branch of my square root. I need to say which way I choose sign in front of the square root. And yeah, we did it, but probably it would be nice to repeat for those who are not used to these things. So when psi is less than k, it should be close to positive real. And when psi is bigger than k, it should be close to positive imaginary. So this is my choice, so I made it precise. Okay, so let's do it. I will probably remove everything. Let's keep the so far. So we have this boundary, the omega 3. And this boundary, the omega 2. So over Green's theorem, I need to define my normal. So here I have normal going like this. So my normal looks inside the domain. I don't remember how we. I didn't check how we introduced Green's theorem in lecture 2 or 3. But of course, if you change the direction of normal, you just need to change a sign in front of the integral. So you should be careful generally, but here it doesn't play a role. So So we have an integration and union of three domains of the following structure. And as I say, we can take all the limits, the integral on this bit will go to 0, so we actually don't have it. And for this bit, like formally, we need to use limiting absorption principle, consider the behavior at infinity, and then we have an exponential decay almost everywhere. And here we have convergence due to mixing condition. So here our integral is just converging. You can also check it by differentiating the mixture series in the vicinity of the edge. So we have a mixture series, we know how our field behaves. We discussed it a lot last time. And this thing basically means that we have integration from minus infinity to plus infinity, and our normal vector is just d for dy, so we differentiate along y-axis. And that's it. Let's compute this thing step by step. We know almost everything we need to know. So what is the normal derivative of our derivative? What is this thing? As I said, I itself reduces to a plane wave. What else we know? We know that U scattered here is 0, and here we have an expression in terms of the plane wave for the normal. For the normal derivative of the scattered field. So and this thing we can reach. So that's what we have. On the left half line we have only the normal part of the field. Then on the right hand side we have unknown field, so we'll just put it down. What else? And we have some expression for normal derivative. Okay, probably will.
Those two attributes.
Yeah.
This is 0.
What?
It's minus 18.
Yeah.
Yeah.
Yeah, it's from minus infinity. So now it's okay. And this is quite a simple integral. And also you can see it converges in infinity. One thing, because it's why it converges, because actually the cosine theta in is negative, since theta in belongs to this segment, and that's why I was mentioning that I only consider angle values in this segment. And okay, let's integrate this. So if we integrate just this bit, maybe I should, yeah, let me just write down the answer. Which is quite expectable. So plane wave just gives a pole, and this is the same way it was for the metric integral. So our forcing generates a pole for the spectral function. And that's it. I will call this thing Wiener-Hopf equation. Okay, let's have a short 5-minute break, and then we will discuss how to solve this equation.